Hi, I am Tom Monnier and I'm going to present our work docExtractor, an off-the-shelf historical document element extraction. After years of massive digitalization, there are now thousands of historical document scans waiting to be analyzed. In the context of a rising interest in digital humanities, the need for easy-to-use and efficient automatic tools has dramatically increased. Document analysis is usually broken down into multiple sub-problems, depending on the task and the document specificity, including handwritten printed distinction, language, or degree of degradation. Recent advances in deep learning enable the development of powerful generic solutions that can tackle multiple analysis tasks with the same core method. However, it still requires training phase specific to each task with appropriate set of manual annotations. Therefore, document analysis systems can still be considered problem-specific, limiting their use in practice and their generalization capacity. Our goal is to develop a single system for generic element extraction that can directly be applied to unseen datasets with strong performances. Our main idea is to leverage the genericity of synthetic data for robust real data applications. To demonstrate the efficiency of such system, we developed a web application where one can browse and select a document, click on a particular page, and view all the generated annotations. We would like to highlight three main contributions in this work. First, we developed a fast and scalable synthetic document generation pipeline. Then we introduced a new ready-to-use system for element extraction that leads to impressive performances on real unseen datasets. Finally, we released a new public dataset dubbed illuSdoc for the fine evaluation of illustration segmentation. Our approach relies on two key elements: a synthetic document generator designed for line-level page segmentation, and an improved UNet-like segmentation network with a ResNet backbone. I am now going to detail the generation pipeline. Our synthetic document generator is a three-step pipeline, each of these steps being fully randomized. First, we create the background image from a set of empty pages. Then we generate the visual content. And finally, we add noise to the resulting document. For the background composition, we collected 177 empty pages that will serve as base. To create various background images, we designed three types of augmentations inspired from real practical cases. The page can be first colorized using a uniform color. It can be duplicated and mirrored, resulting in a double page configuration, which is usually the case for manuscripts. Finally, it can be pasted on a context image to mimic some natural scanning processes. Starting from a composed background image, we generate the document content in two steps. First, we draw a random layout in the empty page. Then we generate elements from a defined set of element types and paste them with random margins. We design four element types frequently observed in real datasets. The image type relies on the Wikart dataset, 8,000 images of drawings and paintings, which we think to be more challenging than natural image datasets for page segmentation. The glyph type is an attempt to mimic illuminations found in manuscripts. To generate a glyph, a random letter is drawn, and it is rendered using one of the 91 highly decorated fonts we collected. The last two element types are drawings and texts. Both element types involve more complex generation and labeling processes I am going to detail. As we didn't find any appropriate drawing datasets, we created synthetic ones from random Wikipedia images for example here a plane. We first apply a line detection algorithm that results in a raw drawing. Then at generation time we apply image augmentations to get more various drawings. For the labeling, we chose bounding shapes computed using closing operations as we believe they generalize better than bounding boxes or contours. To generate text, we collected more than 400 fonts, including handwritten ones, and scraped text from Wikipedia pages. We defined 5 layout constraints corresponding to different elements, which include parameters such as line length, font size, and relative position. By combining these 3 aspects, we can render varied text contents. To increase the diversity, we apply text augmentations including formatting, text translation, underlying, or bounding box addition. We chose to label our text lines using the X-height representation and a border region as shown in cyan and orange. This choice is different from popular text representations such as baselines or bounding boxes. Indeed, we believe it enables straightforward text line extraction while preventing as much as possible overlaps line labels. We also empirically show that X-height representation generalizes much better to unseen data than baselines and that adding border labels dramatically increase performances in both scenarios. The last step of our generation pipeline is to add noise. We implemented 3 types of noise. A Gaussian blur can be applied to the whole image. Structure noises such as lines or random shapes can be added. Finally, we mimic bleed-through degradation often observed in manuscripts by repeating our content generation step with a very low opacity. Using this generator, we have built a 10,000 images dataset that we called SynDoc. Here is an example which contains most of the implemented features. The page background has been pasted on a wood context image. There are 2 paragraphs in English which are colored and justified. There is a 3-column table filled with words and numbers. The title at the bottom has been rendered using a handwritten line font. There is also a vertical caption next to the image, and 5 floating words are drawn at the top of the page. Finally, there is a single image that lies next to a glyph depicting the letter P. Here is a batch of examples extracted from our SynDoc dataset. Note how diversified the documents are. I am now going to detail our method. We tackle generic element extraction as a line-level page segmentation task. We use the UNet with a ResNet 18 backbone optimized with standard cross-entropy loss. We made 2 minor modifications in the raw architecture. We first replaced the max pooling operation in Conv2 as it has been shown to lead to gridding artifacts. We also replaced all bilinear upsampling layers by deconvolutions, which give better results for small objects like text lines. We designed a simple and generic post-processing which removes small regions using an area threshold. We evaluated our approach for baseline detection on CBAD datasets and illustration segmentation on Mandragore, RASP 2019, and ILUISDoc. ILUISDoc is a new test dataset for a more representative evaluation of illustration segmentation. It includes diverse types of illustrations and documents are uniformly gathered by categories. For the baseline detection task, we report results from the popular Tesseract 4 as well as concurrent state-of-the-art methods. We can draw 2 main insights. First, our off-the-shelf approach, that is, the method trained on our synthetic documents only, leads to surprisingly good results. It outperforms Tesseract 4 by a large margin and shows results comparable to the weaker methods trained on real data. This demonstrates that our method, solely trained on computer-generated data, can generalize well to real and complex data. When we fine-tune our methods on available training sets, our results are on par with state-of-the-art methods. This is a strong result, since these methods typically involve very advanced and specific post-processing steps, while ours is very simple and common across all datasets and all element types. We believe our off-the-shelf network can also be used as a strong initialization for fine-tuning. To empirically validate it, we initialized our network with both random parameters and parameters trained on SynDoc, and reported the score obtained when training on varying number of samples. SynDoc initialization provides much better performances with large gaps for less than 20 training samples. We believe it is a very valuable result, since document annotations are cumbersome and highly time-consuming. For illustration segmentation, we compare SynDoc to PubLayNet, a large-scale dataset of modern synthetic documents, and compare our segmentation method to mask RCNN, a detection-based approach used in the evaluation of PubLayNet. Two main insights can be drawn. First, our segmentation approach gives much better results than mask RCNN on all benchmarks regardless of the training data. Then, training on our synthetic dataset consistently leads to much better generalization than PubLayNet. This also shows the huge domain gap between modern and historical documents, and emphasizes the value of our synthetic datasets for historical document analysis. We show some qualitative examples on mlou. The green contours correspond to the ground truth, and the red and cyan regions correspond to predicted illustration and text lines. Note how precise our segmentations are even on the thinner illustrations. To demonstrate our approach applicability, we implemented a public web application that automatically annotates visual elements from any document compliant with IIIF protocol. Here is a quick demo. From a standard Mirador viewer, the user can click on Extract button and fill in a manifest URL to launch the element extraction. From the Home window, the user can browse and look for the corresponding manuscript and select a page to view. The user can toggle annotations and visualize them directly in the viewer. Tags associated to text and images are automatically generated. Annotations are made for all the pages of the documents. Although our approach can generalize to unseen illustration types, in this case diagrams, performances can be greatly improved by modeling more complex elements and more advanced augmentations. Note that our generation pipeline is specifically designed to easily incorporate new types of elements. To conclude, in this work, we presented docExtractor, a single and ready-to-use system that leverages synthetic data to efficiently extract text lines and illustrations from real historical documents. Code, models, and datasets are online. More information are available at our project webpage.